So I'm going to spend today talking about origins from the beginning, and next week Patricia will take us up to today. So here is what we thought was a really nice timeline, and so we we happily stole it and wrote to Eric Chasson at Harvard Smithsonian, the Center for Astrophysics, and said, "Do you mind if we use your timeline?" And he said, "No, not only don't I mind, I'm very happy that you asked," and then sent us all sorts of versions of it. And so I think this is a particularly good timeline of the history of the universe, starting from the very beginning and extending into the infinite future. So talking about different stages, and we're going to focus in on a number of these stages today. The particulate stage, what we're interested in is the interactions of particles from the origin back here, the beginning, the Big Bang. This is really all the Big Bang, but what people tend to call the Big Bang, moving on to the era where we're growing galaxies, growing stars, and we continue to grow stars, growing planets like we are now, the chemistry of planets, and eventually into biology and culture, and then off into the future. So let's start with focusing in on that very beginning period, right at that tip, at the apex of that triangle, the beginning. So we can think here, this is the beginning of the universe. Okay, so we're not quite sure what that means. What does it mean, the beginning of the universe? So the time when space gets created, when all of the places that we can see, all the places that we could see from the places that we can see, all the places that you could see from those places, we imagine those starting then. Before that, if there was a before that, because it may be that time itself is created at that moment, so that there's no sense in which you can talk about before that. So even time itself may start from this point. That's very difficult questions to discuss. Even harder questions to answer from the point of view of really being able to go ahead and do experiments, to test those ideas. Okay? There's a whole kind of subfield called quantum cosmology that tries to apply the rules of quantum mechanics to understanding that very, very initial moment, how the universe emerged out of nothing, or whether it did emerge out of nothing, or how it emerged from something else, or are there more dimensions, and what we're seeing is the beginning of that time is really the beginning of when 3 spatial dimensions started to get big, or many, many different ideas. And the challenge from my point of view is the inability to do experiments to actually tell you whether your answers are correct or not. So I'm not going to touch much on quantum cosmology. We have touched on it a little bit in the past, and that's what this check mark means, that at some point we did have a conversation about quantum cosmology, and if you look back in one of our earlier videos, I think it's something from nothing. We talked a little bit about this, but it's really hard to give definitive answers. There's lots of different stories. They're really nice stories. You can put some mathematics together with those stories, but when it comes down to it, you really don't know how to do experiments to test them. So we're going to look a little bit just after the beginning. So we're going to leave that very beginning part alone, and we're going to ask what happens just after the beginning of the universe. Okay? And what we're pretty sure happened was that just after the beginning of time, just after the beginning of the universe, there was massive inflation. What does inflation mean? It means that space got big really, really quickly. Space started to expand at an exponential rate. Okay? And the universe, in that process, everything that was in the universe, whatever there was, got very far all the particles got very far apart from each other. So the universe became very cold and dark, means empty of light, and empty of everything. So that would be a very boring universe to live in, and it's not one that looks like the universe we live in now. The universe we live in has things in it, like tables and people and stars and galaxies and clusters of galaxies. So what happened is that this period of inflation ended with a reheating, that the energy that was stored in whatever was causing the inflation, and what we think it is the energy of empty space, the energy of the vacuum, was driving this exponential expansion, got released in a process called reheating or preheating, and they're subtly different. And the universe became full of matter and radiation, including something that we hope to see someday, which is the cosmic gravity wave background. So waves of gravity coming from the early universe. And this inflation is something we've talked a little bit about in the past, but there's lots more to say about this, and certainly about the creation of this matter and radiation and the gravity wave background and the prospects for seeing the gravity wave background. But we are still sitting way, way at the beginning, at the point near the point of this triangle. Okay? And what we want to do is we want to look beyond the point of this triangle and look at what happens to the matter and the antimatter that's filling space at that time. Now, the thing is, it is matter and antimatter. So there's this matter, and everyone knows that matter is blue, and there's antimatter, and that's red. And it's going through the universe. It's in the universe, traveling across the universe. And for every particle of matter, there is a particle of antimatter. Now, that's great, matter and antimatter. But the problem is when we look out, we don't see very much antimatter. You're never going to walk down the street, grab onto something, and discover that it's made of antimatter, fortunately. In fact, when we look out, we see almost no antimatter. We make antimatter in particle accelerators, not very much of it, but everything we look out and see, as far as we can tell, is made of matter. So the question is, how did that matter become matter and antimatter, which was in pretty much equal numbers, become just matter? Where did all the antimatter go? How did we end up with any matter? And that's a question that's been around really for about 30 or 40 years at least. I mean, ideas about how we might end up with some matter. It's very hard, in fact, to end up with some matter. Almost always when we look at the consequences of our theory, we discover that instead you end up with nothing, or just tiny, tiny bits of matter and antimatter in equal amounts. So what we'd like to know is how we end up with just matter. And this is called baryogenesis, the making of baryons. Baryons means things like protons and neutrons. And the theory of baryogenesis is fascinating and something worth our exploring at some time. But the problem is, well, not problem, the thing is, even back then, the matter we're making, even when we make the matter back when the universe was probably tiny fractions of a second old, much probably less than 10 to the minus 10 seconds old, billionths of seconds old, this excess of matter over antimatter probably was created. It was massless. Okay? As we've talked about in the past, if matter was massless, then it would move at the speed of light, and the matter in this room is not moving at the speed of light. So at some point, the massless matter had to become massive. And you've heard this name recently, the name of this fellow recently, Peter Higgs. So I'm trying to show you the Higgs field filling the universe, okay? And the thing that the Higgs field does is, as particles are feeling the Higgs field, fundamental particles, many of them get mass, okay? So those quarks moving through the universe, the electrons moving through the universe, when the Higgs field turns on, they all of a sudden stop being massless and start having a mass. Okay? And now we're talking much more about particles that are like the particles in this room. The quarks that are in the protons and neutrons are massive, get mass, we now believe very firmly from the Higgs field. And so we've talked a little bit about that, but it'd be nice to talk some more about it and learn a little bit more about that. But that first day of the universe was a very, very busy day. A huge number of different things have happened in that first day. So first we had the inflation, and then we had the making of matter, and then when the universe was about 10 to the minus 10 seconds old, we went through this phase transition where the Higgs field turned on and gave particles mass. This is very well established physics now, as you can tell from the fact that Higgs, just shared in the Nobel Prize, Higgs and Engler got the Nobel Prize for describing the field and the particles associated with this, what's called electroweak phase transition, the fact that particles get mass from the Higgs field. So that happened when the universe was 1/10 of a billionth of a second old. Ever since then, particles have had mass. When the universe was about 1/100,000th of a second old, it went through another phase transition. And what happened was that the quarks that had been running around were no longer able to move very far away from each other. In fact, they had never been able to move very far away from each other, but they had been piled up so close on top of each other that they kind of hadn't noticed. And now as the universe expanded and tried to pull the quarks away from each other, they said, wait, we can't be alone. We have to be in groups of 3, or we have to find an antiquark. So all of those quarks that were running around got bound into protons and neutrons, which are made of 3 quarks each. So all of a sudden we went from having quarks running around and electrons to having protons and neutrons. Now we're into more familiar types of particles. That happened when the universe was just over 1/millionth of a second old. Now, there's still individual protons and neutrons, not nuclei. And the making of nuclei happened when the universe was between about a second and a day old. So not very many nuclei. The universe on its own in this early stage is not very good at doing nuclear physics. Well, it's actually in some sense too good. What it does is it takes every single neutron almost, lets it find a proton, that makes deuterium, and then it adds another neutron and another proton, and almost all the neutrons in the universe end up bound into helium-4 nuclei. So you have hydrogen, that's protons on their own, helium-4 nuclei, and a small remnant of deuterium and lithium. And that's pretty much all that the universe managed to make in that first day. But it was important that it was able to make those because those become the seeds for later things. Okay. What else goes on in that period? Well, probably sometime in that period, dark matter got made. We're not really sure because we don't really know exactly what dark matter is, or as we've heard in the last few weeks, whether it even exists. But if it exists, and if it's particles, and if it's these things called WIMPs that people look for at the bottoms of mines in South Dakota, then it probably got made sometime around this electroweak phase transition, maybe a little bit later, maybe a little bit before. So dark matter got made. The other thing that happened in that first day was that sometime around the first second, we made what's called the cosmic neutrino background. So neutrinos got released, and if we could see them, if we could build a detector that would measure very low energy neutrinos, we would actually be able to look back to when the universe was 1 second old directly and look out at the universe and see what exactly did it look like in every direction when it was 1 second old. And as you saw the sun setting, that was the end of the first day, and it was good. And we learned some things about that, but there's a lot more that we can think about. So here we are. We've looked at that very beginning of the universe, but we are still just here at this very beginning part, okay? At the end of this kind of particle period. We haven't really built any of the structures that we look out and see around us. We have a one-day-old universe. That day-old universe is full of nuclei, but not very many, mostly just helium atoms and protons and electrons and light traveling through it and bouncing around. You'd think that maybe a year later things would have gotten a little bit more messy, more interesting. But no, the year-old universe is kind of the same, just a little bit, things have gotten a little cooler, things have gotten a little far apart, but the light is still just bouncing around. Well, it really takes until you get to the 100-year-old universe, and she is 100 years old, or was it when the picture was taken, that things start to get a little bit more interesting. And what happens is that when the universe is 100 years old, structures start to grow in the dark matter. The dark matter slowly manages to start to pull towards itself, and we've learned a little bit about dark matter. So all of a sudden, the dark matter starts to be able to move around. Before that, it had been too much dominated by the presence of all those photons and neutrinos. The dark matter wasn't important enough. Now the dark matter starts to be the most important source of energy in the universe, and we start to grow some structures. It's really only when we get to 100,000-year-old universe, what happens then is all of a sudden those protons and electrons, the nuclei and the electrons get attached to the protons and to the nuclei, and the light just keeps going straight through the universe and doesn't scatter off anything, and the universe is transparent, and at that point, it releases the cosmic microwave background, the light that we can see in every direction in the universe. And for a long time thereafter, until now, the universe is slowly cooling. It started off of this, it was about 3,000 degrees, and today, the temperature is only about 3 degrees because the universe has gotten so much bigger. And we look out in every direction, we see a uniform temperature in every direction. And when we look at it very, very carefully, we can see small structures in the universe. Those small structures that we see, those are the remnants of what happened when that dark matter was clumping. So back then, when the universe was 100,000 years old, there was these small clumps of dark matter. Very, very gentle clumps, and they left tiny imprints on this microwave background that we can see in every direction. So here we are. We're almost there. We're almost to the point where we can start to talk about the formation of more interesting structures. Okay? All we've been able to, for that first 100,000 years or so, nearly a million years, is to talk about how particles move around in the universe.
At those stages of transition, that first second,
right,
and the first day, and the first 100 years, about how large was the universe, or how large do we think the universe had reached at that point?
We can't really ask how large was the universe because it may very well be that the universe was infinite. And so the answer was that it was infinite then, it's infinite now, but it's gotten bigger. Okay. Okay, which is kind of, how does something infinite get bigger? Well, what's really happening is, imagine we had two fixed places. So imagine I put two balls sitting in the universe, and I waited and asked, how much do they move apart? That's what I mean by getting bigger. So the space was expanding, but no matter how far I went, I wouldn't fall off the edge, and I wouldn't run into a wall. Okay? That may or may not be true, by the way, and that's something else interesting to talk about that something I work on a lot. So the answer is that the universe, from the time when the Higgs field turned on, for example, until the time till now, has gotten 10 to the 12 times bigger, so 1 trillion times bigger. Okay? So over that period. So that's a factor of 1 trillion. From the time when the Higgs field turned on until those atoms formed, it had gotten about 1 billion times bigger. Okay, so all the time that all the distance, all of the universe that we can see out to the microwave background, so everything that we can measure has been the last factor of 1,000, about 1,100 in expansion. All of that particle era, the period when all these interesting bits of particle physics were going on, when things were getting mass and nuclei were forming and atoms was forming, that was at least a factor of 1 billion of expansion. Okay? And before that, the inflation that went on before that, that might have been many, many, many billions, billions of billions of billions of factors of expansion. So if from the particle physicist's viewpoint, the interesting time was all that period of expansion when the universe was growing by huge factors. But in terms of time, it's been the last factor of 1,000 of expansion that structures, that astronomical objects have been around.
Isn't so much of this based on supposition? I mean, when Claudia Durham talked about extra dimensions, it started me thinking, how do we know there wasn't a bigger universe that burst apart and then came back? That every 1 trillion years or so, it expands to the point of explosion and then reforms. How do we know these things?
What do we really know? Okay, and what do we really have evidence for, and what am I just telling stories about? Okay. So in terms of the physics that we can really test and really understand, starting with that 10 to the minus 10 seconds when the Higgs field turned on, all of the physics after that is incredibly well understood. Okay. So that's one piece. So that part of the physics is understood in laboratories. Okay, so we do experiments in laboratories to test the physics, and then it has consequences, and we can go look at the consequences and see whether they're met. So for example, one of the consequences is, of a little bit later physics, is to tell you how much helium will you make, and how much deuterium will you make, and how much lithium will you make. And then you go out and look, and guess what? We make the right ratios of amount. We make the relative right amounts. So that gives us some confidence that our explanation, our taking of this laboratory physics and putting it up in the sky in the universe really is correct, or at least it works. Okay, it's not. There's no evidence it's wrong. If we ask about what about the part before when I talked about inflation, about this universe growing really, really quickly? Okay? Now that was not just invented just because we had people were sitting around and had nothing to do. It was invented to solve a problem. It was invented to solve a problem that I once presented to you, and I can do in questions. We can do the exercise again at dinner if we want. But it was invented to solve a problem. But it also made predictions, because it turns out that when the universe expands in this way, it actually is noisy. Okay? It causes some sound waves to be created, and those sound waves have particular properties. Now, those properties turn out to be translated in a very precise way into that map, that modeled map that I showed you. The patterns of hot and cold spots, of colors there, should have certain statistical properties that one can go out and measure. Now, these predictions were made in the 1980s, and though we were finally able to make the measurements precise enough to test them over the last 2 or 3 years. And they meet those predictions remarkably well, so that we now, I'd say, where 7 or 8 years ago you could stand up and say, I'm not sure that inflation, whether it's actually the right theory of what went on in the universe when it was less than a billionth of a second old. I think now you're hard pressed to say that, because it's made a successful prediction. It's hard to get that one you can't do, and you can't make the laboratory tests to be confident. But at least you can say, well, it was invented to solve some problems and make some predictions. Those predictions turned out to be correct. Here we are back in this period. We're still hoping to make things that look like the things that we look out in the sky and see. Okay? So nothing I've talked about yet are the things that we look out at night and are able to see in the sky. But we're finally here in this period around 1 to 300 million years after the beginning. Okay? And at this point, the electrons and the protons and the electrons and the helium nuclei have gotten together so that the universe is transparent, and the dark matter, and not only have the dark matter clumped, but the matter, the protons and these nuclei are now able to start falling into the dark matter clumps. Okay? So we have these clumps of dark matter, and they're actually, I say clumps, I don't want you to think of something really small and dense. I want you to think of places where there's a little more dark matter here than there, and these structures are quite large. Okay? But they're there on all scales, and now the matter is able to start moving into these dark matter clumps and forming not just structures in the dark matter, but structures in the ordinary matter. And those structures in the ordinary matter, well, that's interesting, because if there are concentrations of ordinary matter, that has the potential to become something that looks like that, namely a spiral galaxy like the Milky Way. But it's not that yet. Okay. Now, it turns out that before we made things like the Milky Way, we probably started to make some stars. Not stars like the sun, much, much more massive, probably 1,000 times the mass of the sun, maybe 10,000 times the mass of the sun. Stars like that don't last very long, these giant stars. they explode, and when they explode, they leave behind heavier elements. Okay? So not just the hydrogen, helium, and little traces of lithium that were made in the early universe and went into these giant stars, but other elements. Okay? And that's important. We need elements other than hydrogen, helium, and lithium. We're not made of much hydrogen and helium. Well, hydrogen, yes, but not much helium and lithium. We're made of all sorts of other things like carbon and nitrogen and oxygen. And we have a lot of iron around that's important. Where does that come from? Well, it comes from slow processes in burning stars, like those giant stars, but also like the stars we see in the sky now, because those giant stars have all exploded a long time ago. It also comes from rapid processes in exploding stars, in supernovae. Okay? So those leave behind remnants like neutron stars, but those neutron stars are very small fractions of the mass that started out in the star. Most of the stuff gets blown out, and in that blowing up of the star, you get a lot of heavier elements being produced. And you also get cosmic ray collisions in interstellar space making new elements. Okay? So those are the places that we make all of the interesting elements in the universe. Okay? Now, to make galaxies, we need to turn this clumps of dark matter, we call them halos of dark matter, and halos of ordinary matter, the colored stuff, we need to somehow do something with that, because that doesn't look at all like a galaxy. Okay? So we want to turn that into something in which the ordinary matter is kind of collapsed into a disk, say. Okay? And in order to do that, it turns out the dark matter itself can't collapse into a disk. That's probably because the dark matter two particles of dark matter rarely hit each other. They just sit out there orbiting around, and they stay in this big spherical halo or nearly spherical halo running around. But we have to get the ordinary particles, the nuclei and the atoms, down into a disk. And that happens when they crash into each other and are able to release some energy. Okay? So they hit each other, and they send off some light. And in doing so, they lose a little bit of energy. And every time they do that, they're able to settle deeper into the gravitational well of the galaxy. Okay? And in so doing, what happens is this kind of amorphous spherical distribution of matter becomes more like a spherical halo of dark matter and a disk of ordinary matter. Now that's starting to look a lot more like what a galaxy is like. We don't see the spherical halo of ordinary matter. What we see is the disk of the spherical halo of dark matter. We don't see that, but we do see the disk of ordinary matter, and we also see some small amount of matter out in this halo. Okay. Now this also happens on larger scales where galaxies are out there, and they start to merge into clusters of galaxies. A few of them may hit each other, and when they do, they will form a large elliptical galaxy, something that doesn't look like a nice disk galaxy, a nice spiral galaxy. So these would be things like the Milky Way or Andromeda, and these would be elliptical galaxies that sit often at the centers of clusters. And we really see that in the sky. So here is a picture from the Chandra telescope of two galaxies colliding with each other. Okay? And when they do that, they typically turn into one bigger, less beautiful, not a beautiful spiral, they turn into elliptical galaxies. Okay. It's also going on today, so these clusters of galaxies, consisting of many spirals and some ellipticals, okay, they're also falling together and making giant superclusters. And these superclusters are huge. It could take light a few 100 million years to cross them. Okay? And they are just being made today. Okay? If we look out in the universe, we see them. We don't see really bigger structures than this. This is about as big as structures get in the universe. Okay? Now, these galaxies that I've shown you still don't look like this, because these things have gas and dust and that. That's kind of what like these particles of matter falling in. But what about all the stars? Where do those come from? So that's what we'll talk about after this break.
First of all, when you say you're making them today, you won't know that for another several million years from now.
Well, right, what I mean today is like 300 million years ago.
Okay, that's close. That's close enough to
So
today.
for cosmologists, that's today.
Oh, okay.
What I mean is it's an ongoing process, okay? And clusters of galaxies, we look at and we see clusters of galaxies that are billions of years old. We see superclusters that are hundreds of millions of years old. Okay, so they're not really billions of, maybe there's one that's a billion years old, I don't know. But clusters of galaxies, those tend to be many hundreds of millions or even billions of years old. Whereas as superclusters, they really are being formed now in a process that started a long time ago, but really only got going over the last few hundred million years.
Oh, the other question I was going to ask before, what is the confidence level, 95%, 98%, then the first several millionths of a second that all these superinflation was happening and all these other things were forming? What is the confidence level that it actually exists?
Okay, so as we go back in time, I would say the confidence goes down. So the whole thing about nucleosynthesis, about this making of atoms, of heavier nuclei. Okay, let's even start. The formation of atoms, when the electrons bind to the nuclei and release the photons. That is very well established now, because we look at it and we see that light, and the properties of the light are so well described by this really very basic atomic physics. Okay, so so both in the laboratory and in the sky we see that, and that's pretty clear. The making of the nuclei, of those taking the protons and neutrons and turning them into helium, that pretty clearly went on. What might have also, there might have been other things going on that affected it a little bit, okay, that changed the actual results, maybe, but it's pretty clear that went on, because we look at it and we see that there's, for every atom of helium, there's about four atoms. I'm going to get this wrong. One quarter of the neutrons and protons are bound up into helium. Okay, and so that prediction is very good evidence that process went on. That was when the universe was like a second to a day old. You go back and ask about, what about the process where quarks bound into nuclei? Now we have no observational evidence in the universe of that at all. We have no way of looking back to when the universe, no probe that looks back to the universe at that age, none whatsoever. Okay? So all we can do is look in the laboratory and say, this is really well-established physics, this must have gone on, but the details of what exactly that phase transition looked like, what else got made, we don't know, okay? So that's a field of active research, in fact, to try to figure out the details of that phase transition. Go back to the electroweak phase transition, this thing that happened where things got mass, the Higgs field turned on at 10 to the minus 10 seconds. Well, I think we now know that there's a Higgs field and Higgs bosons giving mass to fundamental particles. But exactly what went on in that phase transition, we really don't have we have less of a handle on, because we're only now starting to really probe that fundamental physics in the laboratory. We've discovered the Higgs boson, which is an excitation of the Higgs field, but we haven't really measured its interactions that well. And then how well have we really studied the details of what went on in that phase transition? Not at all. And so there could be all sorts of interesting things going on that we haven't quite figured out right. In fact, we probably have a better handle on inflation than on what's called the QCD phase transition and the electroweak phase transition, just because we actually do have observational evidence of certain things that went on during inflation to make this pattern of sound waves that we see in the microwave background.
Going back to the Higgs field again, do we have any idea of what caused or created the Higgs field?
There is a set of fields in the universe, okay? What I mean by that is there's a field that describes electricity and magnetism, a set of fields. There's a field that describes electrons. There's a field that describes up quarks and down quarks, the things that go into protons. So for each type of particle, we describe those particles we think of as excitations, oscillations in a field. So the fact that the Higgs field exists, asking why does it exist is like asking why is the set of particles in the Standard Model what it is. And that's a great question and a very hard question. And it's a question that a string theorist would be trying to answer. They would be trying to figure out how string theory would end up, for example, giving you the standard model set of particles. Okay, so it's a hard, very basic question that people try to make progress on that so far I don't have an answer for you. And neither do they yet. But then you can ask, okay, given that you have a Higgs field, why did it turn on? What do I mean by turned on? What I mean is, it's like turning on a magnetic field. The magnetic field exists whether you turn it on or not. Okay? Then I can bring a magnet into the room, and the magnetic field will have a non-zero value. So before it had a 0 value, now I bring a magnetic field here, a magnet here, now there's a non-zero value. There's some value to the magnetic field here. So how did the Higgs field go from having a 0 value to having a non-zero value? And again, the answer is speculative. The answer, we think, is that it turns out that a 0 value has more energy than a non-zero value. So it actually, for it to have a 0 value, takes energy. So if I wanted to take the Higgs field as it is and turn it off, I would actually have to put energy into the system. Okay? And that's easy to imagine in the context of writing down a theory of the Higgs field, that it might take energy to turn the Higgs field off. Okay? Now you might ask, well, why was it turned off at the beginning? And the answer is that it turns out that when the universe is full of particles, okay, full of hot stuff with lots of energy, that it can change that fact. It can make it that when there's lots of stuff there, the Higgs field would rather be off. And by rather, I mean that it takes less energy for it to be off. And when all those things go away, it would rather be on. It takes less energy for it to be on. Okay? And that's what we think happened, that we went through a transition where the density of matter got low enough that all of a sudden the Higgs field said, oh, wow, I could give up some energy if I just turned on. Okay, if my value stopped being 0, and that's what we call the electroweak phase transition. Okay, so we are now at the point where we have these things that are like dark matter halos with matter in them. A lot of that matter is sitting in this disk in these forms of galaxies, but it still doesn't look like this because we still have to ask what are stars. Now I told you that we maybe had made some giant stars, but those probably, as I said, only lasted a few million years. Or even shorter, maybe a few thousand years, depending on how big they are. The bigger a star is, the less time it lasts. Okay? So we still need to get to something like that. And that happens in places like this. Okay? So this is a picture of a giant molecular cloud. So you really need the gas to dissipate that energy. Remember I said that when the gas when the gas atoms collide together, they're able to give up some energy. Okay? And that process goes on all over the place in gas-rich galaxies like the Milky Way. So this is called the Eagle Nebula, and it's inside the Milky Way. And what's happened is that you have had collisions of the atoms, in which the atoms hit each other, then they are able to give up some energy by radiating energy away. And they can even form molecules, and those molecules can be dense enough that you now have enough material there that you could form a star. Okay? How exactly you end up then causing this object here to collapse and start forming stars, because that's what's happening here, is that, how much mass is here? Hundreds of times the mass of the sun, maybe thousands of times the mass of the sun is in this cloud. Okay? And what's happening is that something maybe a supernova has gone off, so some other star has exploded and caused a shock wave to travel and hit this molecular cloud, or maybe it's just that certain places in the molecular cloud slowly grew and became dense enough. Both those things can happen, so that eventually you get little pieces of this molecular cloud becoming more and more dense and eventually turning on and making stars. Okay? Now, in fact, we've had main sequence stars since, the universe was about a few 100 million years old. Main sequence stars means stars kind of like the sun, about the mass of the sun, small, a little bit less than the mass of the sun, tens of times the mass of the sun. But stars basically like the sun have been around since the universe was a few 100 million years old, and we are still making them today. Okay? The Milky Way makes about one sun-sized star every year. Okay? Other galaxies make much more. There have been at least 2 generations of such stars. So the sun is not made of primordial material. It's not just made of hydrogen and helium from the early universe. It's in fact probably not even made just from material that came out of one of those giant stars exploding. Okay? Those early giant stars exploding didn't process very much material. They got some things going, but they didn't process a very large fraction of the material. Our sun was probably made from material that already went through other stars. And that's good because we wouldn't be sitting here otherwise. Okay? So all of the material in us, the carbon, the nitrogen, oxygen, had to come from the center of another star. Okay? It had to be burned from hydrogen and helium into carbon, nitrogen, oxygen, and heavier material. Okay? So there's been at least 2 generations. And so our sun is called a population 1 star because astronomers number things backwards. The older stars that were made earlier were called population 2 stars. And those very early massive stars are called population 3 stars. Okay, so our sun was made when the universe was about 9 billion years old. A little bit more, about 4.5 billion years ago. And when a star like our sun was born, it was born first in what's called a protoplanetary disk, which means that there's a central piece of it that's denser and cooler, and it's able to collapse slowly and eventually start to turn on nuclear fusion, the process by which stars burn. And then there's all this material, this gas and dust surrounding that, and it is in the form of a disk, just like the Milky Way spiral galaxies are in the form of disks. Okay? And here is a picture of some stars with their protostars with their protoplanetary disks being born. That have been created. And planets form from the material in that disk. The theory of exactly how they form has changed over time, and we may or may not have it right. But what we believe is that what went on is that there was dust in those disks, and the dust was moving around, and sometimes dust particles would hit each other, and it would stick. And they would keep traveling as a bigger particle and get hit again, and they would stick, and then more dust particles would hit them, and more dust particles would hit, and you'd get bigger and bigger grains of dust growing by accretion into things you might call clumps, and then into things that looked like kind of big rocks called planetesimals, meaning small planets. And here is not a photograph from HST or anything, because we can't look out and see with enough detail into one of these protoplanetary disks that going on. But this is an artist's conception of what that might look like. Okay? And so what we think is that then those planetesimals merged into planets. Now the outer planets, they grew large enough to capture hydrogen and helium. They did that because out there was lots of material and it was cold enough out there. It was outside what's called the frost line. So icy material could accumulate around this dust. They could get bigger and bigger, and eventually they were big enough that their gravity could hold on to hydrogen and helium, and they became the gas giants that we see. Probably on the inner part of the solar system, there were of order 50 to 100 small inner planets that started to migrate in because of drag. They were running into gas and dust on the inner part of the protoplanetary disk, and so they were moving in towards the sun, and they were crashing into each other. And in that process, they were getting bigger and bigger. They were growing. Here is what one of the last of those collisions that we were involved in might have looked like. So something like 50 to 70 million years after this process started, when the Earth was around, it probably got hit by something pretty big, and that's what formed the moon. Okay? So some combination of the material from that object and the material from the Earth as it existed then got thrown out into orbit around the Earth, leaving behind the moon. Okay? So, but our 8 planets are basically in place within 10 to 20 million years of the formation of the sun, or about 4.5 billion years ago. Okay? And so our solar system is sitting here by about 9 billion years after whatever this event was that we might call the Big Bang. Now, what happened to that early Earth? And this is something about which I'm certainly not an expert, but in that first few hundred million years, till about 3.8 billion years ago, the Earth certainly started off molten, and the surface cooled to give a crust. The light material hadn't yet risen to the surface, so that crust was actually quite different rock than we currently have on our continent, on our continental shelves, on our tectonic plates. And it cooled to give a crust despite continued bombardment. In fact, there's a pickup in the bombardment rate after about 4.1 billion years ago until 3.8 billion years ago, so for a few hundred million years. So there were smaller tectonic plates moving much more rapidly over the surface of the Earth than our tectonic plates move now. Lots of volcanoes. And what's really important is that because of the presence of the giant planets, especially Jupiter, as they were going around the sun, there's lots of icy bodies out there, smaller objects that were being hurtled by Jupiter. Jupiter would slingshot them into the inner solar system. And that's important because they would hit the Earth. And that's where the water on the surface of the Earth comes from. It actually comes from the outer solar system. It's not the water that was in here in the inner solar system initially. We weren't able to keep hold of that initial water initially. But that was really pretty quick. By about 4.4 billion years ago, so within the first 100 million years, there's actually evidence that there were already liquid oceans. Okay. So I think there's lots more certainly for me to learn about this, and I'm looking forward to hearing some lectures more about this early period in the Earth's history. So I brought you from a period when we really don't understand what was going on, the very beginning of the history of the Earth, of the universe, about 13.8 billion years ago, when the universe was much more than 1 trillion times smaller than it is now. So, in other words, when everything that you see was much more than 1 trillion times closer together than it is now. 1 trillion is a very big number, and when I say it's much more than 1 trillion, I probably mean it's more like 1 million trillion or 1 billion trillion times closer together than it was. And if this inflation idea is right, it's more like trillions of trillions of trillions of times closer together than it is now. Okay? So we've come from, the universe over that period has expanded by an absolutely unfathomable, really, amount. We can write it down in mathematical terms, but for us to imagine it ourselves is very, very difficult to have a physical picture of just how much the universe has grown. To this point, 13.8 billion years later, where we have a planet that has some land surfaces, it has liquid oceans, it has an atmosphere. It's not an atmosphere that looks like the one we have now. It doesn't have much oxygen in it, for one thing. We couldn't live on that planet. But the stage is set for the next phase, and I hope you'll come back next week to hear about that next phase. Thank you.